For this problem, we have a circuit right here. We are asked what is the value of the current I1 in milliamps. We are to use the following values as what we're given, and we're only given these things. Now, we could solve this using the node voltage method, where we actually look at the node here, we take the voltage across here, and we minus it across the voltage here with this resistor, and so on and so forth, but that's a lot of work. Instead, we can use the mesh current analysis or method. And what this is saying, well, we have this voltage right here. And there's going to be some current that goes out of here and goes this way, and it's going to split like this and like this. It's kind of the idea. Or you could just say that, well, there's going to be some current going around this area inside of this loop, right, like this. This is going to be our I1, and then there's some current that's going to be flowing around this way, and it's going to be going in this loop, which is our I2. Now, for our V1, we know that voltage, the direction is kind of into the positive, out of the negative, if you think of it like that. So it's going to be going this way, and same thing for our V2. So that's the same way, or those are the ways of our voltages. Now, for mesh current, we are first going to take a look at our current. So we have our I1, and I'll write this in a different color. We have I1, and then inside of here we're going to have parentheses, and we're going to add up all of our resistors that are connected to it. So we have R1, we have R5, and we have R3 all in this path. Now, the voltage is going in the opposite direction of our current. We can see that they're going against each other, so we're going to do minus V1. And since it's a minus for V1, that means it is going to be subtracted from here. And just like node voltage, we're going to set all of this equal to 0 when we're done with this. We still have one more thing to do. We know that we have I1 going across this resistor, right? It flows throughout this entire part. Well, I2 flows like this. And if our I1 is going this way and our I2 is going this way, they're going in opposite directions across this resistor. And so what that means is that we are going to have to do a subtraction here. So we have minus I2 across the R5 resistor, and this is going to be equal to 0. Now we have to make an equation for our I2. So let's start off by keeping this in order so that we can use like Symbol Lab and plug it into a matrix. When we look at this, we know that same rules apply. I1 is going this way, I2 is going this way. So we are going to subtract from this I1 across resistor 5. Next, let's look at the voltage, because it's the next thing here. So we can see that V2 is actually going in the same direction as our I2. They're going in the same direction, so we're going to be just adding our V2. So we have plus V2, and again, that's because they're going in the same direction. Now we need to do a plus I2, because this is the side that we're looking at. Everything is relative to our I2. I2 is always going to be positive. And here we have R2 plus R5 plus R4. These are all the resistors that this current flowing through this area is going to be touching, and it's set equal to 0. Now, from here, I'm going to rearrange this just a little bit. So in this next part, we can say that this is kind of like part 1. We write it out. Now we have part 2. I'm just going to write it a little bit cleaner. We are going to have our I1. We're going to have R1 plus R5 plus R3. I like to just use variables until the very end. We have minus I2, R5, and then we're going to set this equal to V1. Now, from here, there's a couple ways we can rewrite the second one. I'm just going to do it where we leave the minus I1, R5 like this. We have our plus I2, R2 plus R5 plus R4, and then we're going to move the V2 over, so it's going to be a minus V2. And now we can take all of this and actually plug it into a calculator, which I've already done right here. So we can see that for the first one, with the matrix, we have, and I'm representing this, by the way, I'm representing I1 and I2 as X. So X is I1 and Y is I2. And we can see our X and Y are right here. And then we have everything related to our I1. We have 8.5, which is our R1, 7.1, which is our R5, I believe. and 10.9, which is our R3, and it's being multiplied by 1,000 for each of these because we're working with kilo ohms. So once we plug everything in, oh, and then this is set equal to the voltages, V1 over V2, and negative V2, and we can scroll down here, and this is going to be the answer. So the X is the only thing that we care about because X is equal to I1. So that means this is going to be equal to 0.00048, and this is measured in amps. Now the question is asking for it in milliamps. So we are going to have 0.00048 amps times 1 milli over 10 to the negative cube, because that's the conversion. And so this is going to come over 3 places. And that just means that the answer for this problem is going to be 0.48, and this is in milliamps. So that's how you go about looking and solving for this problem.